Alright guys, so today we're going to go over some forces. And this is for your force retest. So if you need to retest, this is what you have to bring into me. So forces. So remember there are three laws of forces. I'm just going to go ahead and focus this in real quick. Hold on just a second. Okay. So the first law, Newton's first law, is inertia. An object that is moving will continue moving. Object at rest will stay at rest unless acted upon by an outside force. So state of motion remains constant Okay, remember that is an object at rest will stay at rest, an object in motion will stay at motion unless acted upon by an outside force such as friction or a push or a pull. As far as inertia goes, the more mass that you have, the more inertia you have. It is harder, it requires more outside force to get a refrigerator moving than it does to get a basketball moving. You have to apply more force to the fridge. So the more mass there is, the more inertia. Newton's second law is really just that formula. The force is equal to mass times the acceleration. If you have more acceleration or more mass, you're going to need more force to get those. This is also if there's no acceleration, then the forces must be balanced. Must be balanced. So if you have a constant velocity, let's say 2 meters per second, and you push a box with 3 newtons of force, how much would that frictional force be? Because you have a constant velocity, that means you have no acceleration, which means it has to be balanced. So if you have 3 newtons pushing, you have to have negative 3 newtons opposing. They have to be opposite so that you have no acceleration. Newton's third law is equal and opposite. You kick ball with 6 newtons, ball hits foot with negative 6 newtons, equal and opposite. Now, that ball is going to fly off if you kick it with 6 newtons of force. It's because it's going to have a lighter mass. It can move quicker. It takes a greater force for you to move. All right. So mass, that's an A, does not change. If you have a mass of 5 kilograms, you have a mass of 5 kilograms everywhere. Most people got that confused with weight. Weight does change. Weight is the mass times the acceleration due to gravity. So if you have a mass of 5 kilograms on Earth, your weight on Earth, we're using 10 for simple math, your weight would be 50 newtons. On Pluto, your mass would still be 5 kilograms, but Pluto has a different acceleration due to gravity. It's 5 kilograms times 1.67 meters per second squared. 1.67 is Pluto's acceleration due to gravity. So whatever that would be, I don't have my my calculator. Hold on just a second. It's going to end up being 8.35 newtons. All right, so when you're drawing a free body diagram, I do not want the actual picture. So, free body diagram. No pictures. We only want a box or a dot with arrows. So let's say you have a hot air balloon that has a buoyant force of 3,000 newtons. And it's going to have a mass of 1,200. So, balloon. Okay, buoyant. To be buoyant means you float. So it's a force upwards. So if you're to draw this in a free diagram, I don't want a balloon. I want a dot or a box. Okay, I have a buoyant force up this way of 3,000 newtons. Well, what's my force pulling me down? That's my weight. That's my force from gravity, which would be 1,200 times 10. Newtons. Go ahead and use your calculator just to make sure you don't make stupid mistakes. That would be my free body diagram for that. Okay, now what if I asked you how fast this balloon was accelerating and in what direction? How fast really isn't the right term. I should have said what magnitude, what number, but here we are. So to do that, I'm going to look at my F net. My F net is going to be the sum of all my forces. So I have a 3,000 Newton force up plus 120,000 Newton force down. I'm making it down so it shows me that they're opposite directions. Which tells me that my total forces is negative 117,000 newtons. This is not good if you're in that hot air balloon, I can tell you that much. Hey, guess what I did? I made a boo-boo. Which would make a lot more sense. I added an extra decimal. So we're going to do that, we're going to do that, we're going to do that. It's actually 11,700 newtons, which makes a lot more sense. It's still bad news for this, so that was my bad, sorry. This is important why we use our calculator and take our time. All right, now I need to know how much acceleration I have, though. So I have F equals mass times acceleration. My net force here was 11,700, and my mass was 1200 times my acceleration. So 11,700 divided by 1200. 0, no. Delete that, the last 0. 9.75. And this is a negative, so this is going to be negative 9.75 meters per second squared. That is, it's almost free fall. That's bad news. They better turn on the gas on this balloon. All right. Same thing. If you have a 60 kilogram firefighter and he's accelerating downward at 2.3 meters per second squared. And you want to know what is that frictional force. First thing you gotta do is draw his free body diagram. Okay. The thing pulling him down would be his weight, which would be 60 times 10, 600 newtons. We do not know his frictional force. We just don't. But we know that the entirety of this guy is going downwards at 2.3. So what I'm actually going to do is solve for the total force and then use that to find my frictional force. So this whole thing is accelerating at negative 2.3. So my force on all of them, that F net is equal to negative 138 newtons. Okay, and I know that my F net is equal the sum of all my forces. I now know that my F net is negative 138, and my gravity is 600, and it's going to be also downward, plus my frictional force. So add 600. 462 is my frictional force. So newtons, it is a positive number because it is going upwards. All right, I don't have the boxes printed out, but they will be on your retest. And a lot of people miss them. All right, so I'm going to simulate the boxes on here, but let's say Sally pushed a box. With a weight of 2 newtons. To the right. The force of friction from the carpet is going to be 3 newtons. Now, in this case, with the we saw on a test that looked like this. Okay, each newton I'm going to represent with one block, one box. So I got to draw my free diagram. There's my box. Has a weight of 2 newtons. So that would be one line on my box. 2. She's pushing it to the right. She's pushing it this way. And it's going that way. So you have to have a large frictional force, a large push. And you have a 3 newton frictional. So 1, 2, 3. So while this one, you don't know what the amount is, it has to be greater than 3. So 1, 2, 3, I'll go ahead and add another one for it to be 4. I don't know what it is, but I know it has to be greater than 3 for it to be moving. Because this box is not sinking into the ground, we know that has a normal force upwards of 2 blocks. F normal, F, G, F, F. We're going to call this the force applied, and that would be my box. Now, if she's going to push it and it speeds up, I would draw that one bigger by more blocks. If it ever gets to the point where there's no acceleration, we have that. We have 1, 2 blocks down, 2 blocks up, 1, 2, 3 blocks to the side. This would be equal. My force applied would be equal to my frictional force. That's how it'd be balanced. It would have no acceleration. Remember, an object at equilibrium can still be moving. It's just not going to be accelerating. That's it. You need to bring these in with the tests. Remember, I'm staying after school this week, only 2 days. Make sure you leave yourself enough time to complete the test. And that's all I got. Thank you. There. Don't know why it's doing that. Oh my God, it better have recorded.